Everyone, welcome to the lecture series on advanced structured analysis. Now in this class we will discuss on the analysis of a plane truss using stiffness matrix method. So let us see a plane truss, the pin jointed truss using the stiffness matrix method. So taking the area of cross section for all members is 1000 millimeter square and the modulus of velocity is 200 GPa. So this is the truss where the joint A, B, C and D are the hinged. They cannot displace in X or Y directions. Only joint O can displace in X and Y direction due to the external load of 40 kilonewton and 60 kilonewton. So now the degrees of freedom for this particular structure, the degrees of freedom for structure, if you look at joint A, no degrees, all constant, no degrees, 0 degrees, zeros, only O will have 2 displacement, so 2 degrees of freedom. So now we can take the structure without this load and assign the coordinates. Assume the horizontal displacement will be the coordinate 1 and the vertical displacement will be the coordinate 2. Right? Now this is the coordinate diagram structure. It's very important to write down the coordinate. You can assume vertical to be 1 and horizontal to be 2, doesn't matter, but it's very important to identify. Then write down or calculate the length of each of the members. This is 2.5 and with a 60 degrees, then right. So here then member OA will have length. This is 2.5. So this is 2.5. This is 45 degrees. Right. So this is also 2.5. That means this is root 2 times 2.5. Right. And similarly, this is 2.5 and angle is 30 degrees. So opposite is known to me. So I can find out using sine, the sine 30 equal to 2.5 by the diagonal, which let us say OA. So OA become 2.5 by sine 30. Right? So like this we can find out the length of the each member. Similarly this side. So this length will be again sine 2.5 by sine 60. So OD length will be 2.5 by sine 60. Right? So this will be, this is length OA will be 2.5 by sine 30. So like this we can find the length of each member. We assume that all the loads in the units of kilonewton and millimeter. Then in order to find out the stiffness of each of the members, we will take up a tabular form and then we can assemble the stiffnesses. So this is a column where member identification, and we can find AE by L. All the areas are 1000 millimeter square. E is 200 GPa, that means 2 into 10 power 5 Newton per millimeter square, and length as calculated. So by AE by L, so for OA we get a 40, and for member OB we get 56.569, and for member OC we get 80. and for member OD we get 69.282 is a AE by L factor only. So what is the angle theta for each of the member? This is very important. If I try to draw this structure here, okay, this is A, B, C and D, this is O, and this is 60 degrees, and this is 45, and this is 30 degrees. So what happens here? So this is the coordinate 1 and this is a coordinate 2. So now the angle theta is from the near joint to the far joint. So O is my near joint, A is far joint. So remember something like this. This is O, this is A. Now the angle will be this. So this angle, this is 90 and this will be 60. So this is 150. This is very important to understand. Near end to the far end and taken from coordinate horizontal. Now for OB from this near end to far end, 90 plus 45, which is 135 degrees, and OC it is 90, and OD near into far end, this is the angle. So this will be 60. Now simply AE by L already worked out. Simply cos square theta of this, multiplying this, we get the values here. This is 30 and here 28.285, and here is 0 because cos 90 is 0, and this is 17.321. Here cos theta sin theta will get minus 17.321 minus 28.285, and this is 0 and this is 30. And AE by L sin square theta, just angles are readily available. So this is 10, 28.285, and this is 80.0, this is 51.962. Then we take a sum of this all. When you sum this, so what I get is 75.606. Sum this all, I get minus 15.606. When I sum all this, I get 170.247. Now we know what is K11. K11, that means coordinate 1 is at the joint. There are 4 members meeting here, so that is why we take a sum of all the members K11, that is summation of AE by L cos square theta. This we already did in the table, so this is directly is nothing but 75.606. Then this sin theta cos theta is K12 or K21. K21 is also equal to K12, which is a summation of AE by L cos theta sin theta, which is equal to minus 15.606. Then K22, which is summation of AE by L sin square theta sin square theta, which we got it here as 170.247. So now this is the stiffness matrix. The stiffness matrix for this we got here. Now the what are the directly forces applied on the coordinate direction. So if you look at this previous structure on this direction here, so I have force equal to 40 in coordinate 1 and minus 60 in coordinate 2 because my coordinate is vertical here. So I have to give a minus 60. So P1 and P2 will be equal to 40 and minus 60. So I am taking all the forces kilonewton and displacement in millimeter. So now the stiffness equation, what we have is your K into delta is nothing but my P, right, minus PL because there is no other force in the member. It doesn't induce any other forces. Movement is not there. So directly using this stiffness equation, so K is 75.606 and minus 15.606 minus 15.606 and then 170.247 is the stiffness matrix, and delta, this is delta 1 and delta 2. These are displacement at the joint O, which is equal to 40 and minus 60. So taking the inverse of this K, so I can find out the delta 1 and delta 2 is 1 by AD minus BC, which is 1 by 12628.12 into 170.247, 15.606, 15.606 and 75.606 multiplied by this 40 and minus 60. So multiplying this all, so what I get here, 0.465 minus 0.310, or obtained result will be in millimeter. Very important. That's why I mentioned in the beginning that kilonewton and millimeter is the basic units we are assuming here. That means delta 1 is 0.465 millimeter right hand side direction, and delta 2 is minus 0.3. That means my assumed direction was vertical, so I am getting displacement downward. So since I get it, once displacement is there, simply the member forces can be calculated using the equation which is POA, the force in member AB. So here the force in member OA will be nothing but the formula AE by L into delta OX minus delta AX, near end minus far end. Very important. Near end minus far end. Near end is O, far end is A, into cos theta for member OA plus delta OY minus delta AY into sin theta AOA. Very important. Now look at here. Very important. Far end displacement. So OA, sorry. The far end minus near end. So this some mistake here. Sorry. So this has to be far end. First, this is A, and this is near end A. Similarly here, far end A Y, near end OY. So now AE by L we have a 40. Far end displacement at A 0 minus near end displacement at A is what here? X direction. This is nothing but here what I got is delta sorry, this is OX and this is delta OY. So delta OX is 0.465 into cos theta OA cos 150 degrees plus delta AY, so 0, minus delta OY minus or minus plus 0.310 into sine of 150 degrees. So this gives me the value of equal to 22.308 kN. So this is a force in OA. So now if you take force in POB, so again AE by L delta far end is your B X minus delta OX into cos theta OB plus delta BY minus delta OY into sin theta OB. So this gives me AE by L for this is 56.569 into this is 0 minus OX remains always the same 0.465 into cos theta OB is 135 plus 0 minus plus 0.310 into sine of 135 degrees. So this will be equal to 31.00 kilo Newton. Similarly, POC can be A by L, which is for POC is your 80, and delta here this will not change. The delta BX and delta OX at this case will not change. 0 minus 0.465 times cos 90 degrees, OC remember 90 degrees, plus 0.310 into sine 90. So this will be equal to 24.8 kilonewton, and POD will be A by L for the OD is 69.282 into same 0 minus 0.465 into cos of the angle of OD is 60 degrees plus 0 plus 0.310 into sine 60 degrees. So this will be equal to 2.492 kilonewton. So this is how we find out the member forces for this kind of truss. Thank you.